Okay, let's dive right in. We're about to do a deep dive into aerosol diffusion, really tearing into Chapter 7 of Heinz aerosol technology. The goal here is simple, to give you that expert-level command of this material you're going to need for your PhD defense. By the time we're done, these concepts will be second nature.
Here's how we're going to tackle this. We're starting from the ground up, building a really solid foundation. We'll kick things off with the absolute basics, the motion of a single particle. Then we'll figure out how to put a number on it, see how that translates to real-world movement, and then, finally, get into the practical applications and consequences.
All right, first things first, we have to get crystal clear on the most fundamental concept of all, the huge difference between the chaotic, random dance of one single particle and the predictable, overall movement of a whole cloud of them.
And it all starts here, with what we call Brownian motion. I want you to picture a single microscopic particle just hanging out in the air. It's not still, not at all. It's being constantly and relentlessly pummeled from every single direction by invisible gas molecules. This chaos forces the particle into this jerky, irregular wiggle. That little dance, that is the engine driving everything else we're about to talk about.
Okay, this right here is a distinction you absolutely have to nail for your defense. Brownian motion is the cause. It's that individual, random wiggling we just talked about. Diffusion, on the other hand, is the effect. It's the large-scale, observable result you get when you have a whole bunch of particles and they start moving as a group from a crowded area to an empty one. One is the chaos, the other is the predictable outcome of that chaos.
So, now that we get the concept, the next question is obvious, right? How do we actually measure this? How do we put a hard number on how fast this process happens?
Well, it all comes down to one single super important parameter, the diffusion coefficient, which we just call capital D. But what is D, really? It's not just a letter in an equation. It actually represents a fundamental physical battle that's always going on.
Think of it like this. Small diffusion is basically the outcome of a microscopic tug-of-war. It's a constant struggle between the forces that are trying to push particles forward and the forces that are trying to hold them back.
So on one end of the rope, you've got the driving force. You can think of this as a kind of osmotic pressure. It's that natural push for particles to spread out from a crowded space into an open one. And pulling back on the other end is the resisting force, Stokes drag. That's just a fancy term for air friction, the force of the gas itself that's trying to slow the particle down.
And this is where the magic happens. The Stokes-Einstein equation wraps all of this up into one beautiful package. It shows us that D, our diffusion coefficient, goes up with temperature, which makes sense, right? More heat, more energy, more wiggling. But, and this is key, it is inversely proportional to the particle's diameter. In plain English, the bigger the particle, the slower it diffuses.
And this is the take-home message, the one you can't forget. In the world of diffusion, size is everything. The smaller a particle is, the less drag it feels, and the ridiculously faster it diffuses. And look at these numbers. We're not talking about small changes here. A tiny 0.01 micron particle diffuses 20,000 times faster than a 10 micron particle. That's not a little difference. It's a completely different universe of physics.
Okay, so we've got the wiggles down. And we had this number, D, to describe how wild those wiggles are. But what does that actually mean in the real world? How far does a particle actually travel from where it started?
The path of any one particle? Totally random. You can't predict it. But the average net distance a whole bunch of them travel from their starting point, that is something we can predict. We call this statistical trick the root mean squared displacement.
And this little equation right here, don't let its simplicity fool you. It is incredibly powerful. It connects the average distance a particle wanders directly to the two things we've been talking about, our diffusion coefficient D and time t. It lets us put a real number on how far a particle has strayed.
And this is where the rubber really meets the road. This slide is huge because it puts diffusion in a head-to-head battle with gravity. Just look at this. For a tiny 0.1 micron particle, its random movement from diffusion is over 40 times stronger than the pull of gravity. Diffusion just completely dominates. But for a big 10 micron particle, gravity wins, and it's not even close. This size difference is the great dividing line in the world of aerosol science.
So, that dominance of diffusion we just saw for small particles, it has a massive real-world consequence, one that can make or break your experiments. These tiny particles stick to stuff. They stick to everything.
Here's the fundamental difference you have to get. A gas molecule hits a wall, it bounces right off. No big deal. But an aerosol particle, it hits a wall and it sticks. Game over. It's taken out of the air. This means that right at the surface of any wall, the particle concentration is effectively zero.
So what happens when you have a wall where the concentration is zero, right next to air that's full of particles? You create a steep gradient, and as Heinz puts it so well, that gradient acts like a vacuum, sucking particles out of the air and onto the surface where they get stuck.
You can almost see this happening in slow motion. At just 1 second, a super steep gradient forms right at the wall. Then, as time goes on, 10 seconds, then 100 seconds, this depletion zone, this area of air that's been scrubbed clean of particles, just keeps growing and pushing further out from the wall.
And here's why you, as a researcher, have to care about this. This isn't just theory. If you're trying to sample aerosols through a tube, look what happens. For the tiniest 0.001 micron particles, you lose almost 98% of your sample to the tube walls. They never even make it to your instrument. If you don't account for that, it is a catastrophic experimental error.
Okay, so diffusion can be a huge pain, right? It messes with your samples, it causes you to lose particles, but in science, we love to flip the script. What if we could use this seemingly destructive force as a tool? Well, it turns out we absolutely can.
And we do it with a seriously clever piece of engineering called a diffusion battery. This instrument is designed to do one thing. It takes that predictable particle loss that was causing us so much trouble and turns it into an incredibly precise measurement tool for nanoparticles.
Here's how it works, and it's actually genius in its simplicity. You flow your aerosol through a whole series of screens or tubes. The tiniest, fastest diffusing particles, they crash into the walls and get removed almost immediately. The slightly bigger particles make it a bit further before they get stuck. So by simply measuring what percentage of particles make it all the way to the end, you can work backwards, figure out their diffusion coefficient, and from that, calculate their exact size.
All right, let's wrap this up. For your defense, these are the core concepts you need to have absolutely locked down. 1. Diffusion is the net result of random Brownian motion. 2. The diffusion coefficient d is a tug-of-war between pressure and drag. 3. For tiny particles, diffusion beats gravity, hands down. 4. This dominance leads to massive particle loss on surfaces. And 5. We can cleverly turn that loss into a precise measurement technique.
So we'll end with this. Mastering diffusion isn't just about passing an exam or defending a chapter. It's about learning the fundamental rules that govern the entire world of the very small. When you understand these principles, you hold the key to engineering better solutions for everything, from designing new medicines that can be inhaled deep into the lungs to building the impossibly clean rooms needed to manufacture the next generation of computer chips.